Something is lurking in the dark, silent heart of our galaxy. Deep inside the pitch-black core of the Milky Way, space telescopes have detected a ghostly glow. For decades, it seemed like a localized anomaly, a strange cosmic beacon shining at a very specific energy of 511 kiloelectron volts. This is the exact signature of matter and antimatter annihilating each other in a flash of gamma-ray light. But now, astronomers have uncovered a shocking truth that space agencies kept quiet about. The antimatter is not just staying in the center, it is leaking out. A colossal, invisible stream of positrons is escaping from our galaxy, heading into the intergalactic void. Where is this massive river of antimatter coming from, and why is it escaping? Why does our galaxy seem to produce far more antimatter than all known physics can account for? This is the central dramatic question we must solve today. To understand this mystery, we must look at the ghostly particle that should not exist in such vast quantities. Every single second, the Milky Way is bleeding a staggering 10 to the power of 44 positrons. That is a number so large it defies human comprehension, representing a constant state of cosmic warfare. If you were to travel to the galactic center, you would find yourself surrounded by this invisible, deadly fog of annihilation. How did we miss this massive leak for so long? And what does it reveal about the ultimate fate of our home in the universe? The answer lies in 20 years of satellite data that scientists are only now beginning to fully decode. What they have found challenges everything we thought we knew about the structure of our galaxy. Let us venture deep into the radiation data to see the first clues of this cosmic leak. This leakage suggests that the galactic center is not a peaceful sanctuary but a raging engine. We must question what exotic power source could be fueling this monstrous production. Could it be a sign of a new, undiscovered physical law? Or is it the death rattle of ancient cosmic giants that ruled the early universe? Scientists are baffled, and the silence from space agencies only deepens the mystery. The truth is out there, hidden in the gamma-ray maps. We need to go back to the beginning, back to the first observations that started it all, to truly understand how this cosmic mystery was born in the darkness of space. Only then can we begin to uncover the secrets of the galaxy. Astronomers are working day and night to map these cosmic pathways. They are trying to find where the antimatter meets the normal matter. The resulting explosions create a glow that we can see from Earth. It is a beacon of high-energy physics shining across the vast emptiness of the cosmos. We listen. The evidence begins with a spacecraft that has spent 2 decades staring into the high-energy sky. The European Space Agency launched the International Gamma-Ray Astrophysics Laboratory, known as Integral, to map the most violent events in the universe. On board this satellite is a specialized spectrometer called SPI, designed to detect gamma rays. For 20 years, SPI has recorded the faint, persistent glow of 511 kiloelectron volts. This specific energy only occurs when a positron, the antimatter twin of an electron, collides with normal matter. When they touch, both particles vanish instantly, transforming into pure high-energy light. The satellite data revealed that this annihilation glow is heavily concentrated in the central bulge of the Milky Way. This central bulge is a dense swarm of old stars surrounding a supermassive black hole. The disk of our galaxy, where younger stars and planets reside, shows only a faint trace of this radiation. This distribution presents a scientific headache because the known sources of positrons do not match this shape. In the galactic disk, radioactive isotopes produced by supernovae can account for the faint antimatter signature. But the bright, spherical glow in the galactic center remains unexplained by normal stellar processes. For a long time, scientists assumed the positrons were trapped in the core, held by magnetic fields. They believed the antimatter was produced and destroyed in the same small region of space. But in the year 2026, a groundbreaking study shattered this assumption. By analyzing the high-latitude hotspots in the integral data, physicists discovered that the antimatter is moving. It is not confined to the galactic bulge. Instead, it is escaping into the circumgalactic medium. This discovery suggests that our galaxy is far more active and far more mysterious than anyone previously imagined. We must now trace the path of these escaping particles to see where they go. How did this happen? How could these particles travel so far? The answer lies in the magnetic channels that wind through the galaxy, acting as cosmic highways for the escaping antimatter. This means that our galaxy is not a closed system. The boundaries we draw on maps are meaningless to these high-energy particles. They drift into the intergalactic void, carrying the secrets of the core with them. Researchers are using advanced computer models to simulate these journeys. They want to see how magnetic fields shape the flow of antimatter. These models show complex, winding paths that loop around the galactic disk. It is like a cosmic circulatory system, pumping antimatter out into the deep dark of space. The scale of this process is truly monumental, stretching across tens of thousands of light years. Every data point from the satellite confirms that the leak is real and active. We are wishing the galaxy breathe in a way we never expected, changing our view of the cosmos forever. But then, the mystery took an even stranger turn that stunned the astronomical community. Physicists Thomas Seigert and Hiroki Yoneda decided to look where no one else was looking. Instead of focusing on the bright galactic core, they analyzed the empty space far above and below the galactic plane. There, in the cold void, they detected weak signatures of 511 kiloelectronvolts. This was the first evidence of antimatter annihilation occurring completely outside the disk of the Milky Way. The positrons are somehow traveling thousands of light years away from their birthplaces before they finally collide with electrons. This means the Milky Way is leaking antimatter into the intergalactic void, like a cracked cosmic reactor. If positrons are escaping the galaxy, the total amount of antimatter being produced must be much higher. The researchers calculated that the galaxy produces up to 10 to the power of 44 positrons every second. This massive rate of antimatter production cannot be explained by standard stellar evolution models. How do these delicate particles survive the journey through the hostile interstellar medium without annihilating sooner? Magnetic fields must be acting as giant highways, guiding the positrons out of the galactic disk. These magnetic channels allow the antimatter to bypass dense clouds of gas where they would immediately destroy themselves. This explains how they reach the high galactic latitudes before meeting their end. But this explanation only raises a deeper, more unsettling question that scientists are struggling to answer. What is the engine at the center of the galaxy that is churning out this endless stream? We must examine the competing theories, from dead stars to the most mysterious substance in the cosmos. The conflict between these explanations represents the frontier of modern astrophysics. We must find the source no matter how strange or dangerous it may seem to be. This is where the true detective work of physics begins. We are looking at a process that takes place on scales so vast they dwarf our entire solar system. The discovery of these high-latitude hotspots indicates that the escaping positrons are not just a minor leak. They represent a massive, ongoing transfer of energy from the galactic core to the circumgalactic halo. This halo, once thought to be a calm and empty space, is actually a turbulent zone of matter and antimatter collisions. The gamma rays produced here travel across millions of light years to reach our detectors. They carry the physical signature of the events that created them, serving as cosmic messages. By studying the polarization and energy spread of these gamma rays, physicists can reconstruct the conditions of the galactic center. This research requires combining quantum mechanics with general relativity, pushing our mathematical tools to their absolute limit. The cosmic leak is a laboratory that we could never build on Earth, offering a window into the extreme laws of nature. Yes, the search for the antimatter source has divided the scientific community into competing factions. The first theory suggests that the positrons are produced by exotic, high-energy stellar remnants. Microquasars, which are black holes feeding on nearby stars, can launch powerful jets of plasma. These jets can accelerate particles to extreme speeds, creating matter and antimatter pairs in the process. Another candidate is the population of millisecond pulsars, rapidly spinning neutron stars that generate intense magnetic fields. These pulsars act as giant cosmic generators, spinning out positrons into the surrounding space. But many physicists argue that these stellar sources cannot produce enough antimatter to match the observations. This discrepancy has led some researchers to propose a far more exotic hypothesis: dark matter. Dark matter makes up most of the mass in our galaxy, but its nature remains unknown. Some theoretical models suggest that dark matter particles can collide and annihilate, or decay into normal particles. If they do, they could produce a steady stream of positrons throughout the galactic bulge. This would explain the smooth, spherical shape of the 511 kiloelectronvolt emission in the center. However, this dark matter explanation faces fierce opposition from mainstream astronomers. They argue that we do not need to invent new physics when stellar sources might still work. They point out that our understanding of positron propagation through the galaxy is still incomplete. We cannot confirm dark matter until we have ruled out every normal astrophysical explanation. This conflict is not just an academic debate. It touches on the fundamental laws of nature. The resolution of this mystery could rewrite our understanding of particle physics and cosmology. We are standing on the edge of a major revolution in physics, and the stakes could not be any higher than this. If dark matter is indeed the source, it would be the first direct proof of its existence and properties. We would finally begin to understand the invisible scaffold that holds the universe together. But the opponents of this theory are not easily convinced, and they point to the complex magnetic environment of the galactic core. They suggest that the apparent smooth shape of the emission is an illusion caused by how positrons diffuse through space. The particles could be produced by a few discrete sources and then spread out, mimicking a smooth distribution. This physical debate highlights the difficulty of studying things we cannot touch or see directly. We are forced to look at the indirect clues left behind in the radiation data. Every model we build is a guess, a representation of a reality that remains hidden from our eyes. The scientific camp remains divided, and the tension between these theories grows with every new study. The galaxy is holding its secrets tight, forcing us to look closer and think deeper about the nature of space. We wait for the next clue, now. To resolve this debate, scientists are preparing to launch a new eye into the sky. NASA is currently building the Compton Spectrometer and Imager, a space telescope known as COSI. Scheduled for launch in 2027, COSI will be far more sensitive than any previous instrument. It will map the gamma-ray sky with unprecedented precision, pinpointing the exact locations of positron annihilation. By tracking the path of these particles, COSI will reveal whether they come from point sources like pulsars. If the emission is smooth and diffuse, it will provide strong evidence for the dark matter hypothesis. This upcoming mission represents our best hope of solving the decades-old mystery of the galactic bulge. We are on the verge of discovering the true nature of the Milky Way's antimatter engine. When COSI begins its observations, the cosmic leak will finally yield its secrets to human science. We will know whether we are looking at the decay of dark matter or exotic stellar factories. This discovery will synthesize our understanding of high-energy physics and the evolution of our galaxy. It reminds us that the universe is far more complex and mysterious than it appears. The glowing heart of the Milky Way is not a silent place, but a chaotic laboratory. As we look up at the night sky, we are looking at a galaxy that is leaking antimatter. The next time you gaze at the stars, remember the invisible river of positrons streaming into the void. It is a reminder of the endless mysteries that await us in the deep dark of space. We must continue to ask questions, to explore, and to push the boundaries of our knowledge. Subscribe to join us on this journey as we uncover the secrets of the cosmos. What do you think is producing this mysterious antimatter leak? Share your thoughts in the comments below, and let us continue this exploration together. As we stand on the threshold of this new era, we realize that every answer we find only opens the door to more questions. The journey to understand the Milky Way is far from over, and each step brings us closer to the fundamental truth of reality. The leak of positrons is a reminder of how little we know, and how much is left to discover. The future is bright with possibility, and the instruments we build will help us navigate the dark corners of the universe. We are travelers on a cosmic journey, seeking to make sense of the vastness around us. The mystery of the antimatter leak is just one chapter in the great story of scientific discovery. Join us as we turn the next page, and let us explore the wonders of the cosmos together. The universe is calling, and we must answer with curiosity, dedication, and wonder. Thank you for watching. See you next time. Yes.